For as long as humanity has looked to the heavens, the stars have been our symbols of permanence. They are the fixed points of light in a changing world, the silent witnesses to the whole of history. But this constancy is an illusion, an artifact of our own fleeting existence. Every star, from the smallest red dwarf to the most brilliant blue supergiant, is a finite engine. Every star has a lifespan, and every star will one day die. Tonight, we embark on a journey that spans billions of years. We will witness the birth of stars from clouds of cold dust, and we will follow them through their long, stable lives. Then, we will stand witness to their final, transformative hours. We will see them swell into colossal red giants, cast off their outer layers in breathtaking displays of cosmic art, and collapse into the ghosts they leave behind. This is the story of the end of worlds, the story of how the universe recycles itself. It is the story of our own sun's future. Prepare to journey to the end of a star's life. We begin. Before a star can die, it must first be born. And stars are not born in fire and light, but in the coldest, darkest, and loneliest places in the universe. They are born in vast, interstellar clouds of gas and dust, known as molecular clouds. These stellar nurseries are colossal structures, stretching for hundreds of light years across space and containing enough raw material to build millions of stars like our sun. For eons, these clouds drift peacefully through the galaxy, held in a delicate balance. The inward pull of their own gravity is perfectly counteracted by the gentle, outward pressure of the gas within them. The cloud is a sleeping giant, but this peace cannot last. Something must happen to disturb the balance, to give gravity the upper hand. The trigger could be a shockwave from a distant supernova explosion, the cosmic hurricane from a nearby massive star, or even the gentle gravitational nudge from a passing galaxy. Whatever the cause, a region within the cloud begins to collapse. This is the first moment in the creation of a star. A pocket of gas, still thousands of times larger than our solar system, starts to fall inward on itself. Think of it like a snowball rolling down a hill. As the cloud fragment collapses, it pulls in more and more material, growing in mass. This growing mass increases its gravitational pull, which in turn causes it to collapse even faster. This runaway process is called gravitational collapse. As the gas particles fall inward, they collide with each other, and the energy of their motion is converted into heat. The collapsing cloud fragment, once unimaginably cold, begins to warm up. Over a period of 100,000 years, a dense, hot, spinning heart forms at the center of the collapsing cloud. This is a protostar, a star in its embryonic stage. The protostar is not yet a true star. It is a glowing ball of hot gas, shrouded in a thick cocoon of infalling dust and gas that hides it from our view. Its heat comes only from the friction of its own collapse, not from nuclear fusion. It is like a cosmic ember, glowing from the pressure being applied to it. As more material rains down upon it, the protostar's core becomes ever more dense and ever hotter. For hundreds of thousands of years, the battle between gravity and pressure rages. Gravity continues to crush the core inward, while the heat from the compression pushes outward. Finally, after a long and violent infancy, a critical threshold is reached. The temperature at the very center of the protostar climbs to a staggering 10 million degrees Celsius. At this temperature, the pressure is so immense that the fundamental forces of nature are overcome. Individual protons, the nuclei of hydrogen atoms, which normally repel each other with ferocious electrical force, are slammed together so violently that they stick, they fuse. In this instant, a new, far more powerful source of energy is ignited: thermonuclear fusion. The protostar has become a main sequence star, a wave of energy, born from this new nuclear furnace, radiates outward, blowing away the remaining cocoon of dust and gas. The star, for the first time, shines freely, announcing its birth to the cosmos. The ignition of hydrogen fusion in a star's core marks the beginning of its true life. This is the main sequence, the long, stable, and remarkably peaceful adulthood of a star. For 90% of its existence, a star will remain in this phase, a glowing orb held in a state of perfect, elegant balance. This balance, known as hydrostatic equilibrium, is the single most important concept in understanding a star's life. Imagine a star as the site of a perpetual, controlled explosion. Deep in its core, the nuclear furnace of fusion is releasing an immense amount of energy in the form of photons or particles of light. This outward flood of energy creates a powerful radiation pressure that pushes against the star's own matter, trying to blow it apart. At the same time, the star's own colossal mass exerts an equally immense gravitational force, trying to crush every particle of the star inward into an infinitesimally small point. A main sequence star is a place where these two titanic forces have reached a truce. The outward push of fusion pressure perfectly balances the inward pull of gravity. It is a stable, self-regulating system. If the fusion rate in the core were to increase slightly, the outward pressure would grow, causing the star to expand. This expansion would cool the core, which in turn would slow down the fusion rate, bringing it back to normal. If the fusion rate were to drop, the opposite would happen. Gravity would gain the upper hand, compressing and heating the core until the fusion rate increased back to its equilibrium point. This delicate feedback loop allows a star to burn its fuel at a steady, consistent rate for billions upon billions of years. However, not all stars are created equal. The single most important property that dictates a star's life on the main sequence is its mass. A star's mass determines its core temperature, its luminosity, and, most importantly, its lifespan. The more massive a star is, the stronger its gravitational pull. To counteract this immense gravity, the star must burn through its nuclear fuel at a much, much faster rate. Astronomers classify stars on the main sequence using a spectral classification system. O, B, A, F, G, K, and M. O-type stars are the most massive and luminous, over 30 times the mass of our Sun. They are brilliant blue-white titans that burn with ferocious intensity. Their fuel consumption is so high that their main sequence lifetime is incredibly short, just a few million years. At the other end of the spectrum are the M-type stars, or red dwarfs. These are the smallest and coolest true stars, some with as little as 8% of the Sun's mass. Their gravity is weak, so their internal fusion rate is incredibly slow, like a tiny pilot light. They sip their fuel so sparingly that they can live for trillions of years, far longer than the current age of the universe. Our Sun is a G-type star, a yellow dwarf. It sits comfortably in the middle of this range, burning its hydrogen at a rate that has allowed it to remain stable for 4.5 billion years, with about 5 billion years still to go. For all this time, it has been locked in this graceful truce, a steady beacon of light and warmth. But this truce is temporary. The fuel in its core is finite, and when that fuel begins to run out, the long peace will be broken, and the star will begin its slow, inexorable march toward death. For billions of years, the core of a sun-like star is a fusion factory, converting hydrogen into helium. Over time, the core becomes polluted with this helium ash. Eventually, after about 10 billion years for a star like our Sun, the hydrogen at the very center is completely exhausted. The core is now composed entirely of inert helium. Fusion stops. This is the moment the star's death sequence begins. When the nuclear furnace in the core shuts down, the outward pressure it generated vanishes. The long truce between gravity and fusion is broken. Gravity, now unopposed, wins the battle. The helium core, no longer able to support its own weight, begins to collapse. As it collapses, its temperature and density skyrocket. The core becomes a super dense, super hot ball of helium, smaller than the Earth but containing a third of the Sun's mass. This collapsing core is now like a white-hot poker being plunged into the star's interior. The heat from the collapsing core radiates outward into the layer of gas that immediately surrounds it. This surrounding layer is still made of pristine, unburnt hydrogen. As the heat from the core pours into this shell, its temperature quickly reaches the 10 million degree threshold required for fusion. A new fire is lit, but this fire is not in the core itself. It is in a thin shell around the dead helium core. This is the beginning of the hydrogen shell burning phase. This new way of generating energy has dramatic and devastating consequences for the star. A fusion-burning core is a stable, self-regulating engine. A fusion-burning shell is not. The helium core it surrounds is continuing to contract and get hotter, which in turn dumps more and more heat into the hydrogen shell. This causes the rate of fusion in the shell to accelerate dramatically. The star is now producing far more energy than it did during its entire main sequence lifetime. It is like taking a well-controlled campfire and pouring gasoline on it. The star's energy output soars. This immense new flood of energy pushes outward on the star's upper layers with a force that gravity can no longer contain. The outer envelope of the star, which makes up more than 2/3 of its mass, begins to expand and expand and expand. The star, which had maintained a stable size for billions of years, begins to swell uncontrollably. It is leaving the main sequence and embarking on the next, more spectacular phase of its life. It is becoming a red giant. This is the first warning sign that the star's long, peaceful life is over, and its turbulent end is approaching. The ignition of the hydrogen-burning shell unleashes a torrent of energy that fundamentally transforms the star. The outer layers, pushed by this intense radiation pressure, swell to a colossal size. Over a period of about 1 billion years, a star like our Sun will grow to over 200 times its original diameter. It has become a red giant. The term giant is an understatement. If our Sun were to become a red giant today, its expanding outer edge would swallow Mercury completely. It would then continue to swell, vaporizing Venus. Its fiery surface would reach the orbit of Earth. Our planet would be scorched, its oceans boiled away, its atmosphere stripped, and finally, its rocky surface melted into a globe of magma before being consumed by the star that once gave it life. But as the star expands, a curious thing happens to its surface. The star's energy is now being spread out over a much, much larger surface area. This means the temperature of the surface actually drops significantly, from about 6,000 degrees on the main sequence down to about 3,000 degrees. The star's color shifts from a brilliant yellow-white to a deep, ominous, coppery red. It is a giant, yes, but it is a cool, bloated giant. The star's interior is now a study in contrasts. At its heart is the incredibly dense, Earth-sized core of helium, still contracting and heating up. Around this is the ferociously hot, thin shell of hydrogen fusion, burning at an ever-increasing rate. And surrounding all of this is a vast, tenuous, and relatively cool envelope of hydrogen and helium gas that makes up the bulk of the star's visible size. The star has become a fragile, unstable object. The convection currents within a red giant are slow and powerful. Hot gas from near the hydrogen-burning shell wells up in massive, continent-sized plumes, carrying newly synthesized elements to the surface. This process, known as dredge-up, enriches the star's outer layers with the products of fusion for the first time. An astronomer observing the star would see its chemical composition change, a clear sign of the dramatic events unfolding in its hidden core. Life as a red giant is a temporary, transitional phase. The star is burning through the hydrogen in its shell at a prodigious rate. All the while, the ash from this fusion, more helium is raining down onto the inert core, causing the core to grow in mass and continue its slow, inexorable contraction. The core is becoming hotter and denser with every passing moment. It is a ticking time bomb. The star and the universe is waiting for the core to reach the next critical temperature, the temperature at which the helium ash itself can be ignited as a new source of fuel. For a star like the Sun, this ignition will be an event of shocking and explosive violence. As the red giant ages, its helium core continues to contract and heat up. For millions of years, the core is in a strange and exotic state of matter. The pressure has become so immense that the laws of classical physics no longer apply. The core has become electron degenerate. To understand this, think of the electrons in the core's helium atoms. The laws of quantum mechanics state that you cannot squeeze two identical electrons into the same place with the same energy. As gravity tries to crush the core, the electrons push back with a powerful quantum force. This electron degeneracy pressure is what supports the core and prevents it from collapsing completely. A degenerate core behaves very differently from a normal gas. In a normal gas, when you add heat, it expands and cools. In a degenerate gas, the pressure does not depend on temperature. When you add heat, it does not expand, it just gets hotter. The hydrogen-burning shell continues to dump helium ash onto this degenerate core, increasing its mass and its temperature. The core is now a quantum powder keg. The temperature is climbing steadily toward the 100 million degrees Celsius required to fuse helium. In a more massive star, this transition would be smooth and gentle. But in the degenerate core of a sun-like star, it is a cataclysm. When the core finally reaches the critical temperature of 100 million degrees, helium fusion ignites. And because the degenerate core cannot expand to regulate the reaction, the ignition is not a gentle burn, it is an explosion. In a matter of seconds, across the entire Earth-sized core, the helium fuses into carbon in a runaway thermonuclear event called the helium flash. For a few brief moments, the energy being generated in the core rivals that of an entire galaxy. An immense, brilliant flash of power is unleashed, but it is a silent, hidden explosion. This entire cataclysm is contained deep within the star, completely absorbed by the thick, bloated envelope of the red giant. An observer on the outside would see nothing at all. This titanic flash of energy is finally enough to overcome the electron degeneracy pressure. The core expands, cools, and for the first time becomes a stable, non-degenerate, helium-burning furnace. The star has found a second lease on life. After the helium flash, the star actually shrinks and heats up, becoming smaller and hotter than it was as a red giant. It settles into a new, temporary phase of stability. It now has a core burning helium into carbon, surrounded by a shell that is still burning hydrogen into helium. The star has become a complex, layered nuclear reactor, and in doing so, it has begun the crucial work of forging the elements that are essential for life itself. The ignition of helium in the star's core marks the beginning of a new chapter in cosmic creation. The star has now become an alchemical factory, capable of forging heavier elements. The process by which helium fuses into carbon is known as the triple alpha process. It is a delicate and beautiful piece of physics. Helium nuclei, also known as alpha particles, are stable, but if you try to fuse two of them together, they form a nucleus of beryllium-8, which is incredibly unstable and decays back into two helium nuclei in a fraction of a second. For carbon to be created, a third helium nucleus must strike the beryllium-8 nucleus during that infinitesimally brief window of its existence. It is a process of incredible cosmic coincidence, a three-body collision that must happen at just the right temperature and density. The fact that it happens at all is one of the reasons life exists. Inside the star's core, now a stable furnace at over 100 million degrees, this triple alpha process churns away, converting the helium into a growing core of carbon. Some of this carbon can then fuse with another helium nucleus to create oxygen, another element vital for life. For tens of millions of years, the star exists in this state, quietly manufacturing the building blocks of future worlds and future biology in its heart. The star is now in a phase astronomers call the horizontal branch. It is smaller, hotter, and less luminous than it was during its red giant phase. It has found a new, albeit temporary, equilibrium, but the clock is still ticking. The helium in the core is a finite resource, just as the hydrogen was before it. As the helium is converted into carbon and oxygen, a new inert core begins to form at the center of the star. Eventually, the helium in the core is exhausted. Fusion stops there for a second time, and just as before, gravity takes over. The carbon-oxygen core begins to contract and heat up. This heats the layer surrounding it, which is still made of helium. A new fusion burning shell is ignited. A helium burning shell, located just outside the dead carbon core. And outside of that, the old hydrogen-burning shell is still active. The star now has a truly complex, onion-like structure. At its center is a contracting, degenerate core of carbon and oxygen. Around that is a ferociously hot shell of helium fusion. Around that is a shell of hydrogen fusion. And surrounding all of this is the vast, tenuous outer envelope. The star is now burning its fuel in two shells simultaneously. This new, complex engine is highly unstable, and it marks the beginning of the star's final, dramatic phase of life. The star is about to enter its death throes. With two fusion shells burning simultaneously, the star enters its final stage as a giant, a phase known as the asymptotic giant branch, or AGB. The energy output from the two shells is even more immense than before, and the star swells up once again, becoming even larger and more luminous than it was during its first red giant phase. It has become a pulsating, unstable behemoth. The two burning shells are not stable. They are thin and highly sensitive to changes in temperature and pressure. They begin to burn in a chaotic, alternating cycle. The helium shell will ignite in a powerful eruption called a thermal pulse. This pulse dumps a huge amount of energy into the hydrogen shell above it, temporarily blowing it out and extinguishing it. The star's structure readjusts. Then, after a few thousand years, the hydrogen shell reignites, dumping more helium ash onto the helium shell, which eventually leads to another thermal pulse. This cycle repeats every 100,000 years or so. Each thermal pulse is a violent event that sends a powerful shockwave through the star. These pulses cause the star to pulsate dramatically, its brightness and size varying over periods of months or years. With each pulse, the star's gravity loses its grip on its bloated outer layers. The outer envelope of the star, containing more than half its original mass, is gently but inexorably pushed away into space. This is not a violent explosion. It is a slow, majestic process of stellar evaporation. The star is effectively exhaling its outer layers in a series of super winds. Over a period of just a few 100,000 years, the star sheds its skin, creating a vast, expanding cloud of gas and dust around it. This cloud contains all the elements that were forged inside the star, the helium, the carbon, the oxygen, and releases them into the interstellar medium. As the outer layers drift away, the incredibly hot, dense core of the star is exposed. The core, no longer hidden, shines with an intense blue-white light. It is now so hot that it pours out a torrent of high-energy ultraviolet radiation. This intense radiation slams into the expanding cloud of gas that the star just ejected. The ultraviolet light ionizes the gas, causing it to glow with brilliant, vibrant colors, like a cosmic neon sign. This glowing, expanding cloud of gas, illuminated by the dead stellar core at its center, is one of the most beautiful and celebrated objects in astronomy. It is called a planetary nebula. The name is a historical misnomer. They have nothing to do with planets. They are the final, beautiful artworks of a dying, sun-like star. They are fleeting ghosts, lasting only about 10,000 years before their gas disperses into the galaxy, enriching the interstellar medium with the heavy elements necessary for the next generation of stars, planets, and life. It is the star's final gift to the cosmos. After the beautiful, fleeting planetary nebula has faded into the interstellar medium, the story of the sun-like star is over. All that remains is the object at its center, the naked, exposed core of the dead star. This stellar remnant is called a white dwarf. It is one of the strangest and most extreme objects in the universe. A white dwarf is a cosmic relic of incredible density. It contains about 60% of the sun's original mass, but it has been crushed by gravity into a sphere no larger than the planet Earth. A single teaspoon of white dwarf material, if you could bring it to Earth, would weigh over 15 tons, as much as 3 large elephants. The gravity on its surface is 350,000 times stronger than Earth's. This is matter at the absolute limit. For a star of this mass, the carbon-oxygen core never reaches the 600 million degrees required to ignite carbon fusion. The star simply does not have enough mass to continue the alchemical chain. The nuclear fires are out for good, So, what holds the white dwarf up against the crushing force of its own gravity? The answer, once again, is electron degeneracy pressure. The same quantum mechanical force that supported the core during the red giant phase is now the only thing preventing the entire object from collapsing into a singularity. The star is a quantum object, a single, gigantic atom held up by the strange rules that govern the subatomic world. A newly formed white dwarf is one of the hottest objects in the universe, with a surface temperature that can exceed 100,000 degrees Celsius. It shines with a brilliant, blue-white light, the residual heat from its past life as a stellar core, but it has no internal energy source. It is like a glowing ember taken from a fire. It can only cool down, and this cooling process is extraordinarily slow. The white dwarf is incredibly dense and has a very small surface area, so it radiates its heat away into space with extreme inefficiency. For billions and then trillions of years, the white dwarf will hang in space, slowly fading in brightness and changing in color, from blue-white to yellow to orange, and finally to a dim red. Its ultimate fate is to become a black dwarf. After quadrillions of years, a timescale so long it makes the current age of the universe seem like the blink of an eye, the white dwarf will have radiated away all its heat. It will become a cold, dark, inert sphere of crystallized carbon and oxygen, a planet-sized diamond floating silently in the eternal darkness of the dead universe. This is the calm, quiet, and profoundly lonely end for stars like our sun. They do not go out with a bang, but with a slow, graceful fade into everlasting night. We have followed the long, graceful, and quiet path of a star like our sun as it fades into a white dwarf. But this is only one story, the story of the cosmic average. The universe is also home to titans, to stars so massive and so brilliant they live their entire lives on an accelerated, violent timescale. These are the rare blue-white O-type and B-type stars, celestial monsters that are born with 8, 10, 50, or even over 100 times the mass of our sun. Their lives are not measured in billions of years, but in a fleeting few million. They are the rock stars of the cosmos. They live fast, shine brilliantly, and die young in spectacular explosions. The life of a massive star is dictated by its immense gravity. A star with 50 times the sun's mass has a gravitational force so powerful that its core is crushed to unimaginable pressures and temperatures from the moment of its birth. To fight against this gravity and maintain hydrostatic equilibrium, its nuclear furnace must burn with an intensity that is difficult to comprehend. The core temperature of a massive star is not 10 million degrees, but can exceed 100 million degrees even during its main sequence. At these extreme temperatures, the simple proton-proton chain that powers our sun is inefficient. Massive stars employ a more complex and far more rapid method of fusing hydrogen into helium, a process known as the CNO cycle. In this cycle, atoms of carbon, nitrogen, and oxygen act as catalysts. A proton fuses with a carbon nucleus, which then undergoes a series of transformations, absorbing more protons and releasing energy, until it eventually spits out a helium nucleus and returns to being a carbon nucleus, ready to start the cycle again. It is a far more efficient way to generate energy, like adding a turbocharger to a car's engine. The CNO cycle is so rapid that a massive star can consume all the hydrogen in its core in just a handful of millions of years. Their brilliance is astonishing. A single massive O-type star can be over 1 million times more luminous than our sun. If such a star replaced the sun in our solar system, its intense blue-white light and ferocious ultraviolet radiation would boil away Earth's oceans and strip its atmosphere in an instant. The solar wind from these stars is not a gentle breeze. It is a galactic hurricane, blasting away gas and dust for light years in every direction. Because they burn so hot and live so short, these stars do not move far from their birthplace. They are found in the brilliant, star-forming regions of spiral galaxies, often surrounded by the glowing nebulas from which they just formed. They live and die in the same stellar nursery. Their lives are a frantic race against their own gravity, a constant, high-energy battle that consumes their fuel at a breathtaking rate. They are destined not for a quiet retirement as a white dwarf, but for a final, spectacular act of self-destruction that will forge the heaviest elements in the universe and seed the galaxy for generations to come. When a sun-like star exhausts the hydrogen in its core, it begins a slow, billion-year journey to becoming a red giant. When a massive star exhausts its hydrogen, its end comes much, much faster. The star's immense gravity crushes the now inert helium core with terrifying speed and force. In just a few 100,000 years, the core temperature soars past 100 million degrees, and helium fusion ignites. The star swells, not into a red giant, but into a colossal blue or red supergiant. A star so large it could easily swallow the orbit of Jupiter. But unlike in a sun-like star, the ignition of helium is not the beginning of the end. It is just the next step in a frantic, cascading sequence of fusion stages. After the helium is exhausted, leaving behind a core of carbon and oxygen, the story for a sun-like star is over. For a massive star, it has just begun. Its gravity is so powerful that it can continue to crush the carbon-oxygen core, heating it until it reaches the next critical threshold, 600 million degrees. At this temperature, carbon fusion begins. The star's core becomes a furnace where carbon atoms are fused together to create heavier elements like neon, sodium, and magnesium. This new energy source holds gravity at bay for a few thousand years, a mere moment in the life of the star. When the carbon is gone, the neon core collapses, heats to over 1 billion degrees, and neon fusion begins, creating oxygen and magnesium. This stage lasts for about a year. When the neon is gone, the oxygen core collapses, heats to 2 billion degrees, and oxygen fusion begins, forging silicon and sulfur. This stage lasts for a few months. The star has now become a layered cosmic onion. At its center is the product of the latest fusion stage. Surrounding that is a shell where the previous stage is still burning. Surrounding that are more and more shells, each burning a lighter element. At the very center of the star, a frantic race is underway, with the star fusing heavier and heavier elements in a desperate attempt to generate enough outward pressure to fight off the inevitable collapse. The final stage of this process is silicon burning. After the oxygen is exhausted, the silicon core collapses and heats to over 3 billion degrees Celsius. The conditions are so extreme that the silicon atoms are blasted apart by high-energy photons, and their fragments are then reassembled into even heavier elements, primarily a group of elements centered around iron, including nickel and cobalt. The silicon burning phase is astonishingly brief. It lasts for about a single day. In 24 hours, the star creates a dense, inert core of iron at its center, and with the creation of that iron core, the star's fate is sealed. The frantic race is over. Gravity is about to win its final, most spectacular victory. For millions of years, the massive star has survived by playing a cosmic game of chess with gravity, always finding a new fuel to burn to create the pressure needed to stave off collapse. But iron is the final move. Iron is the ultimate stellar ash. It is the one element that cannot be used as fuel. The creation of an iron core marks the moment of inevitable death for the star, and the reason lies in the fundamental physics of atomic nuclei. Every act of nuclear fusion, from hydrogen to silicon, releases energy. This is because the new, heavier nucleus that is created is more stable and has slightly less mass than the sum of the original nuclei that formed it. That tiny bit of lost mass is converted directly into a tremendous amount of energy, according to Einstein's famous equation, E equals mc squared. This net release of energy is what powers the star. The graph of this energy release is called the curve of binding energy. It shows how tightly bound the protons and neutrons are inside an atomic nucleus. The curve rises steeply from hydrogen up to iron, but iron sits at the very peak of this curve. An iron nucleus is the most stable, most tightly bound atomic nucleus in the entire universe. You cannot release energy by fusing iron atoms together. In fact, if you try to fuse iron into a heavier element, the process doesn't release energy, it consumes it. It takes more energy to force the iron nuclei together than you get out of the reaction. Fusing iron would cool the star's core, not heat it. The same is true for splitting iron apart through fission. That also requires an input of energy. Iron is a thermodynamic dead end. It is the end of the line for stellar alchemy. Once the star's silicon-burning shell has created an inert iron core at its center, there are no more moves to make. The star has no way to generate any more energy to fight gravity. The core is like the engine of a car that has not only run out of fuel, but has seized up completely. The iron core grows rapidly as the silicon-burning shell continues to dump more iron ash upon it. In a matter of minutes, the core swells to a size larger than the planet Earth, containing about 1.5 times the mass of our Sun, all compressed to an incredible density. It is held up only by the quantum force of electron degeneracy pressure, the same force that supports a white dwarf. But the core is still growing. It is approaching a critical mass limit, known as the Chandrasekhar limit. Once the core's mass exceeds this limit, about 1.44 solar masses, electron degeneracy pressure will no longer be strong enough to resist the crushing force of gravity. The core is about to undergo a collapse of unimaginable speed and violence. The moment the iron core exceeds the Chandrasekhar limit, the final, catastrophic act begins. Electron degeneracy pressure fails. In less than a second, the core, an object larger than the Earth, begins to collapse inward under its own titanic weight. The speed of this collapse is breathtaking, reaching over 70,000 kilometers per second, or nearly a quarter of the speed of light. As the core implodes, the density and temperature skyrocket to levels that are almost beyond physics. The iron nuclei are crushed so close together that they are essentially touching. The intense pressure becomes so great that it overcomes the fundamental forces that govern matter. Electrons are physically forced to merge with protons in the iron nuclei, a process called electron capture or inverse beta decay. When an electron and a proton merge, they form a neutron and release a tiny, ghostly particle called a neutrino. This process happens on a massive scale throughout the entire collapsing core. The core is neutronizing, being converted from a sphere of iron into a sphere of pure, tightly packed neutron. This conversion removes the electrons, the very particles that were providing the degeneracy pressure holding the core up. The support is kicked out from under the core, and the collapse accelerates even further. The flood of neutrinos produced in this process is so immense that in these few seconds, the collapsing core radiates more energy in the form of neutrinos than our Sun will in its entire 10 billion year lifetime. These neutrinos stream out of the core, carrying away a tremendous amount of energy. The collapse continues until the core has been compressed from the size of the Earth down to a sphere just 20 kilometers, or about 12 miles, across. It has now reached the density of an atomic nucleus. A single sugar cube of this material would weigh 100 million tons. At this point, a new quantum force, far more powerful than electron degeneracy pressure, finally kicks in. It is called neutron degeneracy pressure. The neutrons resist being squeezed any further. The core can be compressed no more. The implosion abruptly halts. The core, having collapsed at a quarter of the speed of light, suddenly hits the unyielding wall of neutron degeneracy pressure and bounces. Like a rubber ball being slammed against a concrete floor, the core rebounds in a titanic shockwave. The entire collapse, from the size of the Earth to the size of a city, has taken less than 1 second. The stage is now set for the star's outer layers, which are still raining down onto this super dense core, to meet this shockwave and the most powerful explosion in the universe, a supernova. While the core was undergoing its fraction of a second collapse, the outer layers of the star were, for a moment, oblivious. They were still in freefall, raining down onto the now vanished iron core at incredible speeds. Now, these infalling layers of gas slam into the rebounding shockwave from the newly formed neutron core. The collision is apocalyptic. Initially, the shockwave stalls. The pressure of the infalling material is so great that it halts the shockwave in its tracks. For a moment, it seems the explosion might fizzle out, and the star might collapse directly into a black hole. But then, the neutrinos come to the rescue. The immense flood of neutrinos streaming out from the hot neutron core while they rarely interact with matter, are so numerous that they slam into the gas trapped behind the shockwave. They deposit a tremendous amount of energy into this gas, reheating it and re-energizing the shockwave. It's like giving a failing explosion a second, even more powerful detonator. The revitalized shockwave is reborn with unimaginable force. It turns outward and begins to rip through the outer layers of the star. This is the supernova explosion. The shockwave travels through the star's onion-like layers of silicon, oxygen, carbon, and hydrogen at speeds exceeding 10% of the speed of light. The temperatures within the shockwave are billions of degrees, creating a brief, frantic period of explosive nucleosynthesis. The shockwave is so hot and dense that it triggers a final, furious wave of nuclear fusion, creating elements far heavier than iron. This is where most of the universe's heavy elements are born. Every atom of gold, silver, platinum, and uranium on Earth was forged in the heart of a supernova explosion that happened billions of years ago. The explosion is not just an act of destruction. It is the ultimate act of creation. The shockwave finally reaches the surface of the star, and for the first time, the energy of the core's collapse is released into the universe as light. In an instant, the star's brightness increases by a factor of 1 billion. A single exploding star can briefly outshine its entire host galaxy, a galaxy containing hundreds of billions of other stars. If a supernova were to occur within our own galaxy, it would be visible in broad daylight on Earth and would be brighter than the full moon at night. The star's outer layers, now enriched with heavy elements, are blasted out into space, creating a beautiful, expanding cloud of debris called a supernova remnant. This remnant will expand for thousands of years, carrying the raw materials for new stars, new planets, and new life far into the galaxy. The star has died, but in its death, it has seeded the cosmos for the next generation. After the titanic explosion of the supernova has faded, and the debris has cleared, a strange and exotic object is left behind at the center, the crushed, collapsed core of the massive star. Depending on the initial mass of the star, this stellar remnant can be one of two things, each more extreme than the last. For most massive stars, the remnant is a neutron star. This is the ultra-dense sphere of neutrons, just 20 kilometers across, that was formed during the core collapse and held up by neutron degeneracy pressure. Neutron stars are the densest objects in the universe that are still made of ordinary matter. The gravity on their surface is 200 billion times that of Earth. They are so dense that the escape velocity from their surface is half the speed of light. As the star's core collapsed, its rotation speed increased dramatically due to the conservation of angular momentum, just as an ice skater spins faster when she pulls her arms in. A neutron star can be born spinning hundreds of times per second. This rapid rotation, combined with the star's original magnetic field being compressed into a tiny volume, creates a magnetic field trillions of times stronger than Earth's. This spinning, magnetized object can emit powerful beams of radiation from its poles. If these beams sweep across Earth, we see a regular pulse of radio waves, and we call the object a pulsar, a kind of cosmic lighthouse. However, if the initial star was truly massive, more than 20 or 25 times the mass of the Sun, then its core will be too heavy for even neutron degeneracy pressure to support. When the core collapses, there is no known force in the universe that can stop it. The remnant continues to collapse past the point of being a neutron star. Gravity wins its final, ultimate victory. The core collapses down to a point of zero volume and infinite density, a singularity. It has crushed itself out of existence, leaving behind only its gravitational field, now so intense that it has warped space-time into a bottomless pit. It has become a black hole. A black hole is surrounded by a boundary called the event horizon. This is the point of no return. Once anything, including light itself, crosses the event horizon, it can never escape. We cannot see a black hole directly. We can only infer its presence by the way its immense gravity affects the stars and gas around it. The death of a massive star, therefore, leaves behind a cosmic ghost. It is either a neutron star, a city-sized atomic nucleus spinning in the darkness, or a black hole, a hole in the very fabric of reality itself. These remnants are the final, silent monuments to the lives of the most powerful stars in the universe. We have journeyed from the quiet birth of stars in cold clouds of dust to their final, spectacular ends. We have seen that a star's destiny is written in a single parameter: its mass. Low-mass stars, like our Sun, live for billions of years, only to swell into red giants and then gently puff away their outer layers, leaving behind a beautiful planetary nebula and a cooling Earth-sized ember called a white dwarf. Their end is a quiet, graceful fade into darkness. High-mass stars, the titans of the cosmos, live short, brilliant lives. They forge a layered onion of heavy elements in their cores until they reach iron, the ultimate stellar ash. Their death is not a fade, but a cataclysm. They collapse and then explode in a supernova, a universe-shattering event that forges the heaviest elements and briefly outshines entire galaxies. They leave behind the most extreme objects in creation: a hyper-dense neutron star or a space-time warping black hole. These two paths, one of quiet retirement and one of violent self-destruction, are not just endings. They are essential parts of the cosmic cycle of life and death. The elements forged in the hearts of these stars, the carbon and oxygen from sun-like stars, the gold and uranium from supernovae, are cast out into the galaxy. This stardust enriches the interstellar medium, providing the raw materials for the next generation of stars, planets, and, ultimately, life. Every atom in your body that is not hydrogen or helium was created inside the heart of a long-dead star. The calcium in your bones, the iron in your blood, the carbon that forms the basis of your DNA, all were forged in a stellar furnace and scattered across the galaxy by a star's final breaths or its explosive death. The story of the stars is our own origin story. We are, in the most literal sense, the children of the stars. We are stardust, given consciousness. And as we look up at the night sky, we are looking at the engines of our own creation, the silent, brilliant ancestors whose lives and deaths made our own existence possible.